Students, today we discuss about semiconductor devices. First, we take some key concepts related to this topic. The conductivity of the solids can be explained by band theory of the solids. According to band theory, in solids, the discrete energy levels spread into two bands of energy levels. The highest filled band is called valence band. The next higher unfilled band is called conduction band. The valence band and conduction band are separated by a certain forbidden energy region called forbidden energy gap. As you are seeing in the figure, all valence orbits, I can say, all valence orbits in an atom forms a continuous energy band which is known as valence band. Similarly, all conduction orbits, they form a continuous energy band which is known as the conduction band. And the difference between valence band and conduction band is forbidden energy gap. This energy gap is nothing but the minimum energy required to an electron to jump from valence band to the conduction band. As we know that the electrons are present in the conduction band, the material behaves as a conductor. To get the conductivity, the electrons should present in conduction band. The electrons which are present in the conduction band are called free electrons. Based on band theory of solids, solids are classified as conductors, semiconductors and insulators. As you are seeing in the figure, in conductors, if the conduction band and valence band overlap one over the other, then such substances are called conductors. Examples, metals. For example, I can take sodium crystal. The characteristic feature of conductor is having partially filled energy bands. Sodium is a conductor because of sodium 3s is partially filled, but magnesium is a conductor because of overlapping of 3s and 3p energy bands. For conductor, the forbidden energy gap is 0 electron volt as you are seeing in the figure. In case of insulators, if the conduction band and valence band are well separated, that is forbidden energy gap is above 6 electron volt, then such substances are called insulators. I can take diamond as an example. Now we go for the semiconductors. If the forbidden energy gap between the conduction band and valence band is small, it is in order of 0.7 to 1.1 electron volt, then such substances are called semiconductors. Examples for semiconductors are silicon and germanium. For silicon, the forbidden energy gap is 1.1 electron volt, and for germanium, the energy gap is 0.72 electron volt. At absolute zero, semiconductors behaves as perfect insulators. And semiconductors we can classify into intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductors are the conductors which are known as pure semiconductors in which no impurity is added. Extrinsic semiconductors are the conductors in which the impurities are added. Why we are adding impurities to the semiconductor? To change conductive properties of a semiconductor, we are adding the impurities. By adding impurities, the conductive property changes as well. It gets some special characteristics. To take the conduction in intrinsic as well as extrinsic semiconductors, first I take an example, germanium. First we discuss about the conductivity in a pure semiconductor. Suppose if I take germanium, germanium is having 4 electrons in outermost orbit as you are seeing in the figure. Since it is having 4 electrons in outermost orbit, it is not stable. According to octet rule, it requires 8 electrons in outermost orbit to get the stability. So that it shares 4 more electrons with 4 neighbor germanium atoms to get the stability, forming a covalent bond. Like this, the covalent bond will be formed and a germanium crystal lattice will be formed as you are seeing in the figure. Now in this lattice, the electrons which are present in the bonds as you are seeing, they are called bounded electrons, and the space, vacant space, this we can consider as free space or conduction space. If any electron is present in this space, those electrons are called free electrons or conduction electrons. The number of electrons that present in these free spaces that affects the conductivity of a semiconductor. Initially, if I consider the germanium crystal at 0 Kelvin, there is no free electron, hence it is a perfect insulator. Suppose if I give some energy to this, then what happens? The electron will jump from bounded orbit or bounded bonds to free space, so that an electron and a hole is formed. Now the question is, what is a hole? hole is considered to be a particle which represents the absence of electron. That means when an electron jumps from valence band to the conduction band, at that position a hole is forming as you are seeing in the figure. That hole is nothing but causeless, a vacant space which is having positive charge that is equivalent to electron. Simply I can consider hole is an indication that previously electron was there, and I can consider it is a particle which is having an opposite character, that of the electron. Now the holes and electrons are formed in conductor when energy is given. Number of holes and number of electrons formed are equal. Due to these holes and electrons, the conductivity occurs in pure semiconductors. That means in pure semiconductors, the conductivity is due to number of holes and electrons which are equal in number. Suppose if I consider an arsenic is added, arsenic is a pentavalent, arsenic is added to this germanium crystal. Since the arsenic is having 5 electrons, 4 electrons are shared in the bonding, 1 electron is left freely, this electron left as free electron. Like this, so many number of free electrons are formed in the lattice, and due to these free electrons, the conductivity occurs in this crystal. Since the conductivity is due to electrons, electrons are negatively charged particles. This type of semiconductor is known as N-type semiconductor. Similarly, instead of a pentavalent, suppose if I add a trivalent material to the semiconductor as you are seeing in the figure. The 3 electrons are shared in the bonding and 1 electron gap is there. Now to get the stability, it captures an electron from neighbor bond as you are seeing in the figure. When it is captured an electron, a hole will be formed there. Again, to fill this, another electron is taken from another band. Like this, the hole formation will continues in the crystal lattice. Here the conductivity occurs due to the motion of holes. Holes are positively charged particles. Hence, this semiconductor is known as p-type semiconductor. In brief, I can say a pure semiconductor or intrinsic semiconductor is a semiconductor in which no impurities are added. In this semiconductor, the conductivity is due to equal number of holes and electrons. In extrinsic semiconductors, p-type semiconductor, that is due to addition of a trivalent impurity to the semiconductor, due to motion of holes, we get the conductivity. Here I can consider the majority charge carriers are holes. In N-type semiconductors, due to addition of pentavalent material, the semiconductor turns as N-type semiconductor, and in this the conductivity is due to more number of free electrons or majority charge carriers are electrons. This is the classification of intrinsic and extrinsic semiconductors. Now the same thing we can consider on the base of energy band diagram. Now in energy diagram, the same we can explain on the basis of band theory or using energy level diagram. In energy level diagram, in case of intrinsic semiconductor, the Fermi energy level is exactly between valence band and conduction band as you are seeing in the figure. Fermi energy level is nothing but, I can say, the minimum energy required to jump an electron from valence band to the conduction band. Similarly, when you doping is nothing but adding impurities. Already we discussed the doping, the order of doping is for million atoms, 1 atom is added, and in general we add pentavalent impurity or trivalent impurity to a semiconductor. When a trivalent impurity is added to semiconductor, it becomes as a p-type semiconductor. In p-type semiconductor, the Fermi energy level shifts down as you are seeing in the figure. That means it becomes as an acceptor level. The acceptor level is near valence band. Similarly, when you add pentavalent impurity, it becomes as N-type semiconductor. In N-type semiconductor, the donor level shifts towards the conduction band. That is, Fermi energy level shifts towards the conduction band, so that easily it can give electron to the conduction band. This is the classification of semiconductors, pure as well as impure semiconductors. Now the next topic we consider, which is PN junction diode. First we take what is a PN junction. When a semiconducting material such as silicon or germanium is doped with impurity in such a way that one side has a large number of acceptor impurities and another side has large number of donor impurities. Acceptor impurities means it is p-type, donor impurities means it is n-type. The resulting semiconductor is called PN junction. Near the junction, the free electrons from n region migrated towards the p region and the holes in p region has migrated to the n region. This process is known as diffusion. The diffusion is due to the concentration gradient. Due to diffusion, positive ions are left over in the region and negative ions are left over in p region near the junction. These ions are immobile. Due to the immobile ions on either side of the junction, an internal electric field is formed at the junction which is directed from N to P. The no charge carrier region is found at the PN junction due to the combination of electrons and holes, which is called as depletion layer. The thickness of this depletion layer is in order of 10 power minus 6 meters. When the depletion layer is sufficiently built up, it prevents the electron diffusion from N to P side and hole diffusion from P to N side, and it acts as a barrier. The potential difference across the barrier is set up to prevent the diffusion of charge carriers through the junction is called potential barrier or contact potential. The potential barrier for silicon is 0.7 volt and for germanium is 0.3 volt. The potential barrier value lies between 0.1 to 0.7 volt, which depends on the nature of semiconductor, doping concentration and temperature of the junction. It can be presumed to be equivalent to the condenser, in which the depletion layer acts as a dielectric. PN junction diode can be used as a rectifier and detector. The symbol for the PN junction diode is as you are seeing in the figure. The arrow mark indicates the direction of current, and this is P part and this is N part. The PN junction diode can be connected in a circuit in two ways. Depending upon how we are connecting the PN junction diode in a circuit, the conductivity in PN junction diode will be affected. You can connect the PN junction diode in forward bias as you are seeing in the figure. In this case, the positive terminal is connected to the positive terminal of the diode and negative terminal is connected to the negative terminal of the diode. Now in this forward bias condition, the width of the depletion layer or potential barrier decreases. Why? Because suppose if I consider this figure. In this figure, because of this positive terminal, the holes will be repelled in this direction, and because of the negative terminal, the electrons will be repelled in this direction. The width of the depletion layer will be decreased, so that the potential barrier also decreases, and this results the low resistance for the diode, and the flow of electrons from N region to P region and flow of holes from P region to N region is possible, and we get the conductivity. Suppose if I take a characteristic graph for the forward bias as you are seeing in the figure, up to some potential there is no current in the circuit. This potential is equivalent to I can say the barrier potential. After this barrier potential, the electrons or holes can diffuse or can drift from one region to another region, so that we get current. The current increases exponentially as you are seeing in the figure. And I can say in forward bias condition, the flow of current is mainly due to the diffusion of electrons, and in forward bias the diode is having low resistance and high conductivity. And for an ideal diode in forward bias, the resistance is equivalent to 0. Next we go for the reverse bias. This is the reverse bias connection as you are seeing in the figure. In this case, P terminal is connected to negative terminal of the battery and N terminal is connected to positive terminal of the battery. This case is known as the reverse bias. In case of reverse bias condition, since the charge